Hey everybody, this is a video on the heap data structure, and we're going to build it in Java and use it to create a priority queue. And just as a note, this is the last video in the Algorithms and Data Structures playlist, and we're going to move on to something else next after this playlist ends. I hope you join me here, and let's get started. Alright, let's start with what a heap is, its definition. Well, a heap is basically a binary tree with some additional properties, and we're going to look at those additional properties. One of them is a property of about how keys are actually stored in the heap, and to be clear, a heap stores entries, and each entry has a key and a value. And it also has a structural property defined by its nodes, and we'll get to that in terms of what that means. It's not the same as a heap that you may have heard about in Java. The heap that Java uses to store classes, objects created out of classes are stored on the heap. They're referenced there. This is not the same type of data structure as that, but we're going to get to that. First, the relational property I talked about. It's called the heap order property. In a heap, for each non-root node, the key stored at that node is greater than or equal to the key stored at that node's parent. So as you go up the heap from the bottom of this of the heap, which is essentially just a binary tree, as you go up towards the root, the nodes should have smaller and smaller keys. Sometimes this is referred to as a minimum heap or a min heap. If the reverse is true, each parent having a greater key than its child, then it's called a max heap. But in this video, we're going to cover the min heap. And the heap order property is illustrated here. This is actually not a heap, as we'll see going forward, because it doesn't satisfy the other property, the structural property. So all I'm saying here is that this satisfies the heap order, because on the left we satisfy the heap order because each node has a key smaller than the keys of its children. As you can see, 1 is smaller than 3 and 4, which are its children. The node there with key 3 has children of 5 and 9, and so on. But on the right, we don't satisfy the heap order. For example, the root is 9, but has a child of key equal to 8. And that won't work because that no longer satisfies the heap order property. The other property that a heap needs to satisfy is a structural property. It needs to be a complete binary tree. And what does that mean? It means that all levels except maybe the last is filled to its maximum capacity, meaning each node has 2 children, all the way up to the second to last level. At the last level, the nodes are furthest left, meaning if there are leaves that exist on that last level, that none of them are going to be a right child unless they also have a left child. So here on the left we have a complete binary tree because the first level 0, is the root and it's filled, obviously. The first level, which is the second, or level 1, which is the second level, has 2. That's the max it can hold in a binary tree. And in the last, all the nodes are as left as possible. So for example, that last node on the left could not have been a right child because that would not have been furthest left. Now on the right, we don't have a complete binary tree because we have a left node on the left child of the root. But before we fill in the right node, or the right child, we filled in the left child of the node to its right. And so this is not a complete binary tree because not all the nodes are as far left as they could be. So a complete binary tree, to further describe it, it's a heap H with height lowercase h. If the levels from 0 to h-1 have the maximum number of nodes, and all internal nodes are to the left of the external nodes, and there can be at most 1 node with 1 child, and that must be a left child. And here's a graphic description of the levels. So level 0 has 2 to the 0 nodes, which is 1. Level 1 has 2 to the 2 nodes, which is 4. Level 2 has 2 squared nodes, which is... I'm sorry, level 1 has 2 to the 1, which is 2 nodes, and level 2 has 2 to the second power, or 4 nodes, as you can see here. And then when we get to the final level, it could hold a maximum of 8 nodes, but it only holds 5 nodes, but notice that they're furthest left. Also note that the height is not 4. You might be tempted to think that this is a tree of height 4 because there are 4 levels, but the height refers to the spaces between levels, and so there are actually 3 levels here. Interesting to note that you can get the height of a heap given the number of nodes it has by getting the floor of the logarithm base 2 of the number of nodes, and that's the formula. And so, for example, if you have 14 nodes, log base 2 of 14 is equal to 3.8. The floor of that is 3. And the floor function simply gives you the largest integer less than or equal to the number in those brackets. And if you don't have a calculator to calculate the floor of a particular logarithm, then just know you can get it. So a lot of times you can get it, especially if the numbers are small, because you can just say x is equal to log base 2 of 14 in this case, and you're looking for x. Well, mathematically, that's the same as saying 2 to the x is equal to 14. And you can observe that 2 cubed is 8, and 2 to the 4th is 16, and reason that, therefore, x must be between 3 and 4 in order to give you a value of 14. And therefore, the floor of whatever that number ends up being has to be 3. And so this heap of size 14, or 14 nodes, must have a height of 3. Just a little trick there if you don't have a calculator handy. So all that's great. Now, how do we actually build a heap? In Java, you can build one using an array list. And I choose array list because it can grow and shrink in size. Each node V of the tree T is stored in A's index at position of V. And position of V can be defined as follows. If V is the root, its position is 1. If V is the left child of some node U, then its position is twice the position of U. And if V is the right child of U, then its position is twice the position of U plus 1. So once you have position, then you find out, then you store in the array list at that position the left or right child given by that formula. And that may be a little bit confusing, but we're going to go through some graphics here. If you look at this heap here, I've annotated each node with its index. So in the heap, in the array list really, there's an index 0 which we're going to ignore, and we're going to start at index 1. So we have index 1, and its left child then is at index 2, which is 2 times index 1. Its right child is 2 times 1 plus 1, which is index 3. And this is why that formula exists to find the left and right child. If you look again at node index 2, its left child is 2 times 2, which is 4, and its right child is 2 times 2 plus 1, which is 5. And that's why this pattern holds in a heap. And here's a graphic of how things are stored in the array list, given an actual heap with keys in it. So you have key 3 is the root, or the root stores something with key 3, and so on. Well, we have the array list there at the bottom in the sort of array format. And I said earlier we're going to ignore key 0. And the reason is if you're trying to find the left key or the left child of something at index 0 and you multiply by 2, you're going to get 0 again. And so you can't have the left child of the node be the node itself. And so we don't use index 0. We just leave it empty when we build a heap using an array list. And so now you see everything is indexed from 0 to 7 in this 8 element array list. And really the heap is only stored in indexes 1 to 7. And at 1 we have 3, then 5, 4, 8, 6, 9, 10, going left to right and top to bottom, as you see in the heap above. And if you'll note, the last index is the number of nodes in T. So if it's indexed from 0 to 7, then 7 is the number of nodes in the tree. And here what we have is a visual depiction of each node and its left and right children. And so what we have is, for example, at index 1, we have a node with key 3, and it has a left child of 5. And if you look below with the blue arrow, it has a right child of 4. If you look forward at key with the value of 4, it has a left child at with a value of 9 and a right child of a value of 10 with a value of 10. So now everything is referenced inside this array list, and that's how this array list stores all the values in the proper order of the heap that we see here. So let's look at what happens when you're trying to insert a new entry into a heap that already exists. So here we have a heap with the key and value pairs listed in each node. And I want to insert the entry with key 2 and value y. You can't simply just add to the end of the array list that node, because this would violate the heap order property possibly. And what you'll have to do is take a look at this thing you just added. The entry with key 2 needs to rise higher in the heap because there are clearly nodes above it that have smaller keys. So we need an algorithm. And whenever you insert a new node or a new entry, you need to apply this algorithm. So we'll say we add something to the heap, and then you want to do what's called up heap bubble with that position of v. So pass the position of v to it, and then call up heap bubble. And that's what it's called when you try to take something with the lower key and bring it up higher. And the way you might want to do that is set its position to the current, some variable current, and then while wherever you are, that current has a key that's less than the key of the parent, swap the key with, or swap that node with the one above it with its parent, and set that one you just swapped, the yellow one in this picture, to the new parent, or to the new current, and then continue until the one above that node is no longer less than the parent. So in practice, this is what it looks like. I compared 2 and 19. 2 is less than 19, so I swapped those. I compared 2 and 6. 2 is less than 6, so I swapped those. And then I've compared 2 and 3, and 3 is less than 2. I'm sorry, 2 is less than 3, so we swap those. And then the heap order property is restored. So every time you insert a new entry, you have to do that up heap bubbling to make sure that the order is maintained, to create, to keep it a minimum heap or a min heap. Now, removing the root is the same as removing the entry with the smallest or minimum key, and that should look familiar because that's exactly what you do with the priority queue. Therefore, you can use a heap to create a very efficient priority queue. And we're going to do that in this video series as we go forward. Now, just as before, when we added a node, that wasn't the end of the story, and the same is true here. If you remove a node, you need to replace it with something else, and then you need to resatisfy the heap order property again. But the way you do that is, let's say you take the minimum entry, the root, and you store it in some variable pot. Then you set the root equal to the last entry. So in this case, it would be, I think, 9x is the last entry in this picture here. So then what you need to do is down heap bubble the position of the first entry, or the root. So once you replace the root with the last element, then down heap bubble is called on that root element. Then once all that down heap bubbling is done, return the popped value, or the popped entry. After all, that's what we're using this for, is to get what the minimum value is out of it. Down heap bubble is then presented below. And what we do is we'll say if the node is not external, in other words, you haven't already reached the end or the bottom row, set the left equal to the position of the left key and set the right equal to the position of the right key. Then find out which child is smaller. So if you look at the picture on the left here, 5 is less than 6 is what it would do the comparison on. And then whichever child is smallest is the one you set to the swap position. Once you look at those, once you determine which one has the smaller key, then you're comparing the actual node that you need to move to the one that was smaller in the previous test. So check the position, and if its key is greater than that of the swap position's key, then you swap those and then recursively call down heap bubble onto the swap position. And so using this recursive algorithm, you should essentially end up with the heap with the heap order property resatisfied. So let's look at this. Graphically, if we're trying to remove an entry, we take that node at the root and we store it in some variable v, suppose. And then the arrow on the right that says move to root, you take the last node and put that as root. And so now you have this configuration. And then you start comparing. 9 is, we find first that 5 is less than 6, so you're comparing 9 and 5, and you swap those because 9 was greater than 5. And then you should stop, because you can compare 15 and 10 is smaller, and then you're comparing 9 and 10. And you can stop because the heap order property is satisfied. No need to keep going further because 9 is already less than 10. And you're done with that bubbling procedure, and then all you got to do is return the node you just popped from the root back to the calling function. Perfect. So with all that in mind, let's go ahead and get started and try to build this out in Java. I'm going to use IntelliJ IDEA, so let's start that now. Okay, so I have IntelliJ IDEA open, and I'm going to create a new project. And I'm going to just click Next, Next, and in here I'm going to just title the project Heap and click Finish. And we have an empty project. And what I want to do first is create a heap class. So I'm going to say new Java class and call it heap with a capital H. And we can begin. I did say we're going to use an array list, so I do need to import the array list class. Import java.util.arraylist. And we can just start right here. What we're going to need to do is define sort of the properties of the heap, and then the constructor, and then some functions for inserting and removing, just like we've done in previous projects. That's sort of the flow here. First things first, I'm going to need the actual array list variable, something to hold the heap. So I'm going to say private array list, and I could use generics here, for example, some object of type T and call it heap, but because I'm not that interested in that, I'm just going to make it of type entry. And you might say, what's type entry? Well, I'm going to create an inner class of type entry. And I'll do that right now. Actually, one more thing I need to define is the front of this list, so I can conveniently reference the thing I'm going to pop. So I'm going to say private static final int front equals 1. So anytime you need to pop, you just pop the front. Okay, so back to the inner class, I'm going to create class entry. And this might look strange because we've defined a public class, and inside we have another class. And the reason I'm doing this inner class is because the entry is so closely related to the heap that they may as well just, one may as well just be a property of the other. And it's going to contain a key and a string called a value. And it's going to have its own constructor. And the way you're going to create it is you're going to pass some sort of integer and some sort of value to hold, and that'll hold wherever you create the object. And you're going to set key equal to new key and value equal to new value. And just like that, you can create an inner class that will hold entries. So every time you create an entry object, it'll reference this, and then you can store it inside the array list called heap. Now we can go ahead and create the constructor for the outer class, class heap. And in its constructor, you set heap equal to a new array list. And remember, this is going to store entry objects. And then just to initialize it, I'm going to say add a new entry. And I need some dummy value for the entry at index 0, because we're not going to use 0, as you recall. So I'm just going to put a dummy value in there that's obviously a bogus number. So I'm going to say integer dot min value, and that's whatever's the minimum integer that Java can store, and just give it a string of asterisk. So that's what's stored in index 0, which we'll never care about because we're never going to use it. All right, so we've got our heap created. Anytime you instantiate a heap, this is what you'll see. And a couple things. Array list initially starts, when you create an array list with no arguments, it will have a capacity of 10 to begin with, but it will grow as needed. The other thing is, notice I didn't say heap with square brackets. So you can't reference a heap like this. That's how you reference arrays. And remember, with an array, you might say heap at index 0 equals some value. But you can't do that with an array list. An array list, you can add things to an array list using the add function, as I've done here. So there's some important differences between the array list and the array. Now that we've created the heap constructor, we can jump right in and start declaring and defining functions for finding different things. For example, it'd be good to know if you it would be good to be able to find the parent of a node given its position. And so, and you do that by returning the position divided by 2. And you might think to yourself, well, what happens if you have an odd number? Because if the position is 4, obviously the position of the parent would then be 2. And the answer is, we're using a little bit of a trick here. Because if you're at node position 5 and you divide by 2, and you're storing that answer in an integer, because that's what we're returning here, then it won't return 2.5. It will return 2. In other words, the index 4 and index 5, when you divide either by 2 and store the value in an integer, you're going to get 2. Because it will, if you try to store 2.5 in an integer, like for example, if the position is 5 and you divide by 2, it will just truncate that 2.5 to just 2. So this is convenient. We're using that fact to make sure that any two nodes next to each other that are children of the same parent, when you divide by 2 for their index, you'll get the same parent. And that's why we're doing it this way. We'll probably want to know what the left child is given some position. And so for that, you can just return 2 times the position. And we'll call this right child. And it'll return twice the position plus 1, just as we discussed. We'll need to know if something is external. Is external. Again, we're taking position, and we're going to return position greater than or equal to the heap size over 2. Now, why would we do that? Because the heap size is the total number of nodes that we have, including the one at index 0. And if you divide that by 2, then you're going to get, if it's greater than half the heap size, then you're already at the last level, and therefore you have an external node. And you can verify that by looking at a few examples. I won't be using time here to do that. You probably need to know if there is a left child or a right child. Has left child. And again, you're going to take position, and you're going to return left child of position is less than or equal to the heap size minus 1, which is the last index. So if the heap size is 8, heap size minus 1 would be 7, which would be the final index of this array list. So you're basically, to know if something has a left child, you're just returning whether or not the left child of the position, which is an integer, by the way. In other words, if you take the position, take twice that position, you got to know if that's less than or equal to that index, whatever it ends up being, if it's less than or equal to the last index, and therefore it would have a left child. And then we want to know again, if you have a right child, has right child, take a position, and then return right child of the position is less than or equal to the heap size minus 1. So now we should get to the meat of it, where we're actually inserting nodes into the array list. So I'm going to create one here, a function called insert, and it's going to take a key and a value, and you'll just simply add to the end of the list a new entry based on that key and value. But then remember, I said you had to upheap bubble, and I'm going to upheap bubble the heap.size minus 1. So we're passing the final index and upheap bubbling, and I'm going to comment this out because we haven't defined upheap bubble, so we don't get an error. And then when we're done implementing upheap bubble, I'll uncomment that. Okay. So then next I want to do the remove public string, remember, because it's going to return, you could have it actually return an entire entry, but I'm just going to have it return what was popped. So I'm going to say public string remove, and we don't need to pass any arguments because remove means get rid of, pop the smallest or minimum value node off the heap, or the one at the root, in other words. So entry pop is equal to heap.get front, and that's why we define front. So now we're storing whatever's on the root in popped, so we can return it later. And then you're going to set the front equal to whatever you get at the end of the heap. So you're taking the front, whatever was at the front, and then setting its value, setting its entry equal to whatever you get from the heap's last entry. And then you want to remove the thing at the end, because you already moved it to the top, to the root. And then we want to down heap bubble, which we also have to define, starting at the front. And I'll comment that out because we need to implement it later. And remember, the last thing we want to do is return something. And what I want to do is return this string. I want to return popped.key plus some comma and plus popped.value plus end parenthesis. And you can format however you like, but that's how I want it to look when I pop something. The key value pair inside parentheses. All right, so moving right along, we can start defining the functions we wrote algorithms for. For example, upheap bubble and downheap bubble. Let's start with upheap bubble. Private void upheap bubble. And you're going to take a position of some kind. And we're going to set the current is equal to position. And then while heap.getCurrent.key is less than heap.getParent of current.key. Swap, and here's another function we have to define, current, parent, current. And then you're going to set current equal to parent, current. So this is an effective way of programming. Like, I don't need to know the details of upheap bubble yet, or downheap bubble, or swap. I just need to know where those things are going to go in the main program, and that's what I've done here. And I've commented those out for implementation later. It's very useful for organizing your thoughts and making sure you don't miss something. Okay, so we've implemented upheap bubble, and now I can uncomment upheap bubble, and there's no error there because now it knows what to reference. What's next is I need to implement downheap bubble. Void downheap bubble int position. And now you're going to check if it is not external. In other words, you haven't reached the last row. Then you're going to do a bunch of actions. What you'll want to do is create a swap position integer variable. And I should know which one is smaller, of the left position or the right position of the one you're passing to this function. So int left position is equal to heap.get left child of the position and get its key. And we're going to do same thing with right. And then if the minimum of left position and right position is equal to right position, then what you want to do is set swap position each child of the position, because you're just trying to get the index, which one is smaller, because you're going to swap with the smaller child, if you recall previously in the video. Okay, else swap position is going to equal the left child. Then, once you know which one is smaller, the one on the left or the right, then you're going to say if heap.get position.key is greater than heap.get swap position.key, then you're going to swap position and swap position, and then downheap bubble on the swap position, just like we outlined in the algorithm. All right, so far so good. Looks like we have not, I can uncomment downheap bubble here because it's already been implemented. Looks like swap is the only thing we haven't implemented. So we can go ahead and do that. And it's a pretty straightforward small function. Private void swap first position int second position. What we're going to do is say entry first is equal to heap.get first position. It's an entire entry, not its key, but the entire object, the key plus the value. And in heap.set first position equal to heap.get second position. So take the second and put it wherever the first was, and then heap.set second position equal to the first, which is an entire object, the entry, which is what this thing is storing. So this should swap everything out, and now I can uncomment the swap function. And so far, I think we're done. Oh, wait, there's one more thing we got to do. I just remembered. We won't know if this is working unless we print it out. So we need some way to print out the heap to make sure everything is being done properly and working. So I'm going to go in here and type public void print. And I'm going to say size is equal to heap.size, so I don't have to keep calculating it. Store it in a variable. And then I'm going to say for I equals 1, I less than or equal to size over 2, I plus plus. So for this range of indexes, and I'm only going to go to I is less than or equal to size over 2 because once you get to that point, all of the nodes have been referenced in one form or another, and you don't need to go any further. And that's one of the advantages of having a heap. It's very efficient in some ways. So for that range of indexes, I'm going to say parent is equal to parent, and I probably should define parent. And while I'm at it, I should define all of the other strings. String parent, left, and right. So define a bunch of strings. Parent is plus heap.getI.key plus comma space plus heap.getI.value plus end parenthesis. So parent will equal that. Then if has left child, so if there is a left child, then what we want is left to equal another string. And what I'm going to do is copy the parent string and modify it so there's less typing. And then else, if it doesn't have a left child, then what I'm going to say is left is equal to left child asterisk. All right, and the same thing with the right. So then finally, we want to be able to print the entire string. If, so what we want to do is system.out.println parent plus maybe a semicolon plus left plus semicolon, just to separate it, plus right. Okay, so through the for loop, it's going to print out a row of, it's going to print out the parent, the left child, and the right child of the nodes as it goes forward. And that should work. Actually, I just realized something. We don't want this thing to print an asterisk for the left child. If there is no left child, I don't care. So maybe what we want is instead we should qualify this and start with an if statement. If has left child I, then perform this action. That way, if we don't do that, you're going to have the last print out say that, okay, here's a node and it has no children. Well, I don't care because that doesn't tell me what's in the in the heap. It doesn't add any additional information because that node that has no children would already be printed out earlier because it will be the child of some other node. Okay, so this should actually do what we want it to do. I think we've implemented everything that we need to in the heap. I'm not seeing anything else that we need to write in here. So the next thing to do is create an application that uses a heap. So let's do that. I'm going to go to source and click new Java class, and maybe we'll just call it heap app. And so in here, I can just go ahead and start creating one. PSVM, public static void main, heap, and lowercase heap is equal to new heap. And then we're just going to start inserting things. Heap.insert, and maybe we'll insert for E, and then I'll copy that down several times and modify that, and so that we have some varied values. Okay, so we've inserted everything. Probably makes sense to do a quick print and see what we have started with. So I think we have enough to actually run the program and get some meaningful output. Let me double check what we've done in the heap app. Everything looks good. Oh, one more thing maybe I want to do here, and it would make sense, is to put some separation between the output console's top window and where we actually start printing something. Because otherwise it looks kind of bunched up. And so here I'm just going to say system.out.println. Okay, let's run this and see what happens. Let's take a look. All right, so we've actually printed the heap. And if we look at it and compare it to what we actually entered, this is kind of interesting. We entered 4E, then we entered 7F, then 13Z. But look what gets printed. It says, because you might think looking at it that we entered 4E as the root, 7F is the left child then, and 13Z would be the right child, and so on. But what ends up happening is we have parent is 4E, left child is 7F, right child is 12M. How did that happen? Well, because every time we insert, this program is going to up heap bubble. Remember that, so that it maintains the heap order property. And if we look at this sort of graphically, I can show you why it's doing that. So let's do that now. So if we break down what was happening with the heap we just built in the code, what we started with was we added 4E to the heap. And then we added 7F to the heap, which you can see here as the left child of 4E. Then we added 13. So far, so good. Then we added 11, then 60J, and then 12M. And something interesting happens, because now the heap order property is no longer satisfied, because 12 is less than 13. So those get compared, up heap bubbled, and 12 replaces 13's position. And then 12 gets compared to 4, but it's not smaller than 4, so it stays where it is. So in other words, the heap order property is maintained at this point. Then we move on. 100A is inserted, 55P, 74R, no problems. Then we insert 29T, and again we have a heap order issue, because 29 is less than 60. So 29 gets compared to its parent, which is 60, and they swap because 29 is less, and 29 is already greater than 7, so nothing else needs to be done there. And that's the end of it. We've built the heap in this way, and visually you can see why you see the order that you do on screen. Looking again at the output here, we see that 4E has a left child of 7, right child of 12, 7 has 11 and 29 as children, 12 has 13 and 100, and so on. So this perfectly aligns with what should happen to maintain the heap order property. So everything seems to be working correctly. Let's run some more tests, because we haven't actually removed anything, so let's try that. So I printed everything, and then let's do system out, print line, popping the minimum value. And we're just going to say heap.remove, because remember, this will return a string that shows what we've removed. And then we're going to print the heap again. So basically, we're going to remove 4E and see what the heap looks like once that's done. So I go to run heap app, and there we have it. So we pop the minimum value. Now 7 becomes the parent, because we took, initially we would have taken the last value, which is, I believe, 60J, and put it up back at the top, but then that has to be down heap bubbled. And so that's what you're seeing here. And you can draw this out and verify for yourself that if you remove 4E, this is the heap that you would get, and that should help in being instructive for you. But let's continue and maybe copy this down a couple more times and see what happens. All right, so we did it a few more times, and if I sort of expand on this, we see that we have the initial heap. We remove 4 echo, and then 7F becomes the minimum value. We pop 7 and 11 becomes the minimum. We pop 11 and 12, and so on. So it appears to be working, and you can verify that by drawing this out yourself and see what happens when you pop elements and do the down heap bubble. And so, you know, congratulations, it's working perfectly. What happens if we add another heap element? And I say 1Q. That should be at the top because it has the minimum value, even though it was the last one added. Let's see what happens. And that works out as well. And now 1Q is the root, and then you see what the heap looks like now. So yeah, we're finished. I hope this makes a lot of sense and you got something out of this. Let's go back and conclude. Okay, so in review, in this video, we've created a heap and used it to implement a priority queue in Java. And heaps are very nice for logarithmic time operations that you can do on them. They have two critical properties, the heap order property, which we discussed, and we use the heap order property to create a minimum heap, where the nodes have keys that get progressively smaller as you go from the external nodes up to the root. And we noted that the structural property that a heap has is that it's a complete binary tree, and we describe what that is in terms of how many nodes each level has. We implemented the whole thing in Java using object-oriented programming, and the data structures that are particular to this implementation are the heap, the binary tree, and the array list. And we talked about how those things interact to create this heap. So, congratulations. That's the end of the algorithms and data structures playlist that I've created here and that we've walked through video by video. And some of the things we covered, I wanted to just touch on, the major things we talked about is we talked about using pseudocode to organize your thoughts before writing actual code, and that can help you write much more quickly and be less frustrated. We talked about recursive algorithms, otherwise known as recursion, where a function can call itself, and we used that, even in this video, we used it when we did the downheap bubble implementation in the code. We talked a little bit about the time and space complexity of different algorithms and what order n and order n squared might mean, or an order log n. We talked about sorting algorithms like insertion sort, bubble sort, merge sort, quick sort, and others. We've built linked lists, the singly linked list, the doubly linked list, the stack, the queue, the hash table, the binary search tree, the priority queue, and finally the heap. So, that's a lot to cover. And if you've gone through these videos, well done. This is something you should be proud of. These are the fundamentals of programming in any language for any reason. And if you understand this, you can be sure that future programming challenges won't seem as bad. They'll seem pretty easy to you if you can understand these videos and you've walked through them, because these, like I said, are the foundations of programming a computer chip, of programming a desktop application, a mobile app, or a web application. And so where do we go from here? Well, what you can do is spend more time on algorithms and data structures and learn on your own, because this is not the full story. There are many other algorithms and data structures and ways of analyzing and optimizing different approaches. There's a whole mathematical discipline behind the optimization of these algorithms. And I encourage you to look into that if you're interested. This is not the place for that, because I'm introducing programming to you all using sort of a broad brush survey approach of some major ideas and some great examples. So if you want to go deeper, you can, and I would encourage that if you're interested. And like I said, we're at the end of this playlist, so what's next is a new playlist. And in the next playlist, I'm going to be diving into web development. And web development involves, several things: the front end, the back end, several development tools, and some specific technologies I've listed here. So for front end, we're talking HTML, which is hypertext markup language, which is what you see when you open a website. When you're seeing words and images on a website, often that's there because the HTML is there to present it to you. JavaScript is what makes the web come alive, because JavaScript can be used to add interactivity to website. Without it, or something like that, your web pages would just be text and static images, and that is not very pleasing to look at, or not very engaging. And in the early days of websites, you saw a lot of that. You don't see a lot of static websites anymore because of JavaScript and because of what that affords you. And we'll talk about JavaScript frameworks as well. And JavaScript frameworks are basically ways to write your code much more quickly. The back end means databases and application programming interfaces, and they drive everything in terms of capability. Because without the back end, you basically have a fun or nice looking website that doesn't do anything useful for you, or very little that's any use. You're not going to have users log in. You're not going to be able to access a database and get prices or inventory of your store if you're running a store on a website and so on without a backend. And we're going to be using several development tools. Two I will call out right now are Visual Studio Code, which is what I tend to use to write websites, and the command line. And the command line is in Windows would be your command prompt. In Mac, you might have an application called Terminal or even Hyper or some other command line tool. It doesn't matter which one you use. So you can choose the one you want, but we'll get into that in the videos. Some specific technologies we may be looking at are obviously HTML and JavaScript, but also cascading style sheets, CSS or React, which is a JavaScript framework, MongoDB, which is a database backend, Firebird, Postman, which is used to test your API, Heroku, MariaDB, Next.js, which is another JavaScript front-end framework. So we may use all of those, some of those, and additional ones not listed here. But the basic idea is we're going to be looking at front-end and back-end and how they interact and how you can use those to build websites. Once again, congratulations. Thanks for watching this playlist. I hope you got something out of it. If you have any comments, make sure to leave those in the comments section. And I hope to see you in the next playlist. And take care.